Hello, Professor Polytoad here, and let's talk about geology. Today, we're looking into space and how celestial objects have affected the geological history of the Earth. Specifically, today we're talking about meteorites and the formation of the moon. But realistically, before we can talk about those, we first need to look at how the solar system and Earth formed. Because life on Earth didn't exist during its formation, we don't have a 100% understanding on how Earth formed, but we can look at some of Earth's oldest rocks to paint a clear picture on its formation. The oldest rock on Earth is the Acasta gneiss, found in the Northwest Territories, forming 4.03 billion years ago. Other oldest rocks found on Earth are 3.8 to 3.4 billion years in age, and the interesting feature of these old rocks is that they are sourced from the metamorphism of sediments deposited in shallow water, as opposed to being from metamorphosed primordial Earth crusts, showing Earth's history began long before these rocks formed. The oldest mineral on Earth are zircons in sedimentary beds found in Jack Hills, Western Australia, forming around 4.3 billion years ago based on radiometric data. Because of the hardness and durability of this mineral, it typically isn't affected by weathering and will be removed from the rock it originally crystallized in. This weathering eventually destroys the host rock and releases the zircon. The source of these zircon crystals in Australia is unknown, as the original hosting rock has been weathered away, and the Jack Hill zircons were incorporated into the younger hosting sandstone beds. Here we have examples of the oldest rock and the oldest mineral on Earth, but they formed from processes that predate the formation of the rocks themselves. Earth is always changing from the movement of continents, and this movement is very destructive towards the evidence of events that happened in the far distant past. So, we need to look more outwards for a better understanding of how the solar system formed. Specifically, we need to investigate space for the answer. Out in space, there are a few different sources of data we can observe, and these are from meteorite analysis, looking at areas in space where planets are made, and theoretical modeling. Although these sources provide effective data for modeling the formation of the solar system, it's important to note that any of these sources by themselves would not be sufficient to produce a refined enough interpretation. Arguably, meteorite data is the most important when modeling the formation of the solar system, as typically the meteorites that reach the Earth's surface formed at the same time as the solar system. This age range can be seen in radiometric data within the meteors by analyzing the half-life decay of 238 uranium to 206 lead in zircons, or the 40 potassium to 40 argon decay in silicate minerals. Because these meteors formed at the same time that the solar system did, they represent the general bulk composition of elements within the solar system during its formation. And to talk about meteorites, let's bring out Minior. Minior is a rock and flying Pokemon introduced in the Sun and Moon games, and appears as a rocky star shape. What makes Minior interesting, though, are the colorful inner cores found within, one for every color of the rainbow, and the shiny if you want to count that. In real life, there are only 3 types of meteors, and they're classified based on the iron-nickel content of the meteor's composition. Stony meteorites, which are some of the most important for geochemistry, originally forming from the outer crust of small planetary bodies. They can contain small inclusions of silicate minerals like olivine and pyroxene within the matrix called chondrules, making the entire meteorite a chondrite. These chondrites typically predate the formation of the planet and have a similar bulk composition as the Sun, as they formed at the same time during the same event. Chondrites are also used as a geochemical standard to compare with other rocks on Earth, looking at the various alterations that have affected the rocks over time by using the chondrite data as a base point, and to see variations between rocks similar in appearance and geochemistry. The matrix of these meteorites is rich in organic carbon molecules, something that has created erroneous speculation about the presence of life in meteorites. Not to disprove Deoxys, but life most certainly originated near hydrothermal vents on the seafloor. These meteorites account for 85% of all discovered meteorites, and we can also get achondrites, which are stony meteorites without these chondrules, which are important because they typically originate from the Moon, Lunaites, or Mars, SNCs. Iron meteorites, where 90 to 95% of these meteorites are iron, with the remainder being nickel and other trace elements. These meteorites originated within the cores of small planetary bodies and exhibit Thomson structure patterns due to the extremely slow cooling of the metals from a molten state in the vacuum of space. This slow cooling forms the iron and nickel into this pretty cross-lattice shaped pattern. Stony meteorites are meteorites that contain equal parts stone and iron from the other 2 types, and are thought to originate from the core mantle boundary of the parent planetary bodies. They can further be broken into 2 categories: pallasites, which have large olivine crystals growing in a fine-grained iron-nickel matrix, and mesositerites, which have a striking black and silver matrix with irregular breccia textures. Luckily, we were able to find chondrite that was old enough to date the solar system, and the Canyon Diablo meteorite was able to confirm that the solar system formed 4.6 billion years ago based on lead ratios found in sulfide minerals present.
Hello everybody, welcome to Bell Park, right on the edge of Ramsay Lake and right in the heart of Sudbury, Ontario. This plaque here right behind me shows the Sudbury Basin. If you remember in my Geology of the Sino and History region, I briefly mentioned the Sudbury Basin as a meteor impact, and that's what this map is showing right here. So about roughly 1.8 billion years ago, this giant rock, about 10 to 15 kilometers in size, came down and impacted into the bedrock. In this map right here, this giant circle is the crater itself. So Sudbury is famous for its nickel mining as well as copper, palladium, and other different platinum group elements. And that's found within here because in this ring, because when the meteor impacted the bedrock, it caused a bunch of shock melting, creating a giant pool of magma. And this magma is right along the edge, and within that shock melting is what that fluid began to crystallize the most of our nickel, a lot of copper, as well as palladium and platinum groups. That's it.
$4.6 billion years ago is a long time, but now that we have the Earth's age, let's finally look at how the Earth formed. Starting 4.6 billion years ago, a large cloud of gases and interstellar dust began to collapse into itself due to its massive gravity. This event formed the Sun. The collapse also caused a ring of 100 astronomical units to wrap around the forming Sun with the remaining material. This material began to slowly collide with each other, forming roughly kilometer-sized planetesimals around 4.567 billion years ago. These planetesimals began to further collide over time and form into the larger planetary embryos over millions of years, which are theorized to be the final building blocks of Earth. These planetary embryos are structurally more like planets as opposed to the smaller planetesimals, which refers to the formation of a solid inner iron core within these bodies, and a more silicate-rich mantle situated above. Going back to the different types of meteors, the stony meteorites formed in this area of planetary embryos because of their high abundance of silicate material, iron meteorites formed in this area because of their high abundance of iron and nickel, and stony iron meteorites are thought to have formed at the core and mantle boundary because of their equal parts of silicate material and iron and nickel material. Accumulation of these planetary embryos continue to form the Earth, and this brings us to the formation of the Moon. Analyzing lunaites from the Moon, as well as analyzing rocks gathered from the multiple trips taken to the Moon starting in the late 1960s, it was determined that the Moon formed 4.424 billion years ago, as well that Moon rock and Earth rock have similar oxygen and tungsten isotope data, suggesting a relationship to their formation. The most widely accepted theory of moon formation is that of a large impact during planetary embryo accumulation of a planetary body named Theia, quite possibly the largest and last of these events, where an embryo roughly 10% Earth's final mass impacted a roughly 90% completed Earth. This impact event led to the merging of Theia and the primordial Earth and a formation of a disk around the now molten Earth. The quick accumulation of roughly 1,000 years of this molten ring material formed the Moon. Now, let's talk about the other meteorite Pokemon, Solrock and Lunatone. These rock and psychic Pokemon were introduced in Ruby and Sapphire, and have a very striking resemblance to both the Sun and the Moon. And unlike Meteor, we can assign different types of meteorites to these Pokemon. Beginning with Lunatone, this Pokemon has been confirmed to be a meteorite from its various Pokedex entries, as they state it was originally found at a meteor impact site. Because of its moon-like appearance, we can assume that Lunatone originates from the Moon, thus making it a lunite, a type of achondritic stony meteorite that originates from the Moon but lacks the geochemically important chondrule inclusions within. Solrock is just rumored to have come from the Sun, according to the black and white Pokedex entry, but we can just assume that this is another meteorite, as it is a rock Pokemon and we don't typically get meteorites from the Sun itself. Because of its striking sun-like appearance and the rumors of where Solrock originates, we can assume that Solrock is also a stony meteorite with the presence of chondrules. Chondrules have the same composition as the Sun because they formed during the same event the Sun formed in. So we can say Solrock is a type of chondritic stony meteorite. If the Pokemon world was a real place, I would use Solrock to understand the formation of the entire solar system, and I would use Lunatone to understand the formation of the Moon specifically. But we aren't done yet. The final question when understanding Earth's formation is the solid iron core, and how that formed. Silicate material and iron material are thought to be immiscible to each other, much like oil and water, and the iron-rich core and the silicate-rich mantle boundary form because of this relationship. Planetary embryos are structurally like that of planets, meaning they are present with a separated iron core and silicate mantle. The accumulation of these planetary embryos allowed for the higher density iron material to sink to the center of the molten primordial Earth, where the lower density silicate material remained above. There are two thoughts to how this formed. The first being where the iron collected from embryo accumulation will sink to a certain point, reaching equilibrium with the surrounding mantle material, and further sinking to the center. The second thought is that the iron material sunk rapidly, mere hours after impact, and not reaching equilibrium with the surrounding mantle material. Regardless of the formation model, the accumulation of the higher density iron material from planetary embryos is what forms the iron core, and the solid nature of the center is due to extreme isentropic forces that are enacted upon the iron, which freezes the iron regardless of high temperatures. Understanding the formation of Earth's core is very important, as the core generates the Earth's magnetic field, as well as maintains mantle convection, which controls volcanic activity, earthquakes, and the movement of plate tectonics. To be very, very brief, Earth formed from the accumulation of a bunch of rocks and dust for millions and millions of years, going from dust to planetesimals to planetary embryos and ending with the Earth itself. In terms of geological history, the amount of time this primordial Earth is present is very quick, as this sliver for the Hadean eon represents this primordial Earth, and quickly goes into the Archean and Proterozoic eons. In total, these 3 eons represent 87% of the entire geological history of the Earth, where the remaining 3 eons contain the Cambrian explosion of life diversity, dinosaurs, the emergence of humanity, and the expression of more modern geology. This represents the remaining 13%. But the Archean and Proterozoic eons and their transition into more modern geology can be left for another day. So, why exactly did I want to talk about space in the first place? Not only is this a cool subject to talk about, but also because of the asteroid Bennu and the secrets this rock contains. I've been following this story for a while, and this is super cool. Bennu is an asteroid that formed in the belt between Jupiter and Mars and was discovered by scientists in 1999. NASA became interested with the physical characteristics of the rock, notably the carbon-rich and water-rich composition, and sent a probe to collect samples in September of 2016. The thought was that Bennu could contain answers to the origin of life. The probe reached the asteroid's surface in 2018 and arrived back on Earth in September of 2023 with the collected samples. What they found was a significant number of clay minerals and water-altered minerals, indicating the asteroid came from a water planet. The presence of phosphate minerals as well shows there were water evaporation processes that occurred to crystallize these phosphates. Nothing conclusive can be made, more work needs to be done on these samples, but the environmental formation for this asteroid is strikingly similar to Saturn's moon Enceladus. Arguably, the most important space Pokemon is Deoxys, so let's talk about life. I mentioned before that life originated on the sea floor near volcanic hydrothermal vents deep in the ocean. These vents pump many different minerals and chemicals into the water that fuel the necessary chemical reactions for the evolution of life. And currently they foster unique environments to support many unique and different species of ocean worms and crustaceans. But Deoxys came to Earth on a meteor. So what's up with that? The theory of panspermia is the thought that life came to Earth on a meteorite from somewhere else in the universe. Although possible, asteroids like Bennu do have potential for having some trace of biological activity within, but it doesn't answer the question of the origin of life, merely places it on another celestial body. The ideal place for the evolution of life, as we know it anyways, are near these hydrothermal sea vents on the ocean floor. I don't disagree the potential that an asteroid may have impacted a primordial Earth, thus seeding life, but where did that life on the asteroid evolve from? Otherwise, thanks for checking out my video. It's super cool that we can use space to talk about the geological history of the Earth. And, if anyone is curious, the first undisputed evidence of life was found 3.49 billion years ago with stromatolites, which are just layered carbonate reefs formed from photosynthetic microorganisms. Super cool.